Good. So yesterday we were able to have the our element of our straight wire, and if we looked at a point y from the straight wire P and at an orientation phi, and we just take at an orientation is element of magnetic flux density B, and if this was our x, so that we have our I and our j, we ended up getting our B as being the same as mu naught I over 2 pi y. Okay? Good. And we agreed that we will do the example 2, the next example where we apply Biot-Savart law. This is by looking at the magnetic flux density, the distance away from the coil of radius either R or A, and then we find the magnetic flux density there. So that's so about 20 minutes. I'll eat in 20 minutes into your marathon. So is my lunch, because when I play at 20 minutes, I find that the salads are already finished. They're always nice. So we are losers both. So this is magnetic flux density. Magnetic flux density at a point on the axis of a circular coil of radius A and the distance x and the distance x from the coil, from the center of the coil. It's more or less like the vision of the electricity and magnetism. So I'll draw our coil, and I'll put a couple of other strands to make it a coil of n times, a couple of them, another couple of them. If you add another strand, another strand, so that we look at it as a coil of n times. Could have more than 4, got 4 strands, but we can take as many as possible. So this is the center, and it is of radius A, and then we have its axis, along its axis, a distance x from the point P where an electromagnetic flux density is felt, and that electromagnetic flux density felt here is due to an elemental part of the coil. So I'll draw, and then I take the this to be our R. This is our dB prime. This is our dB. So let's take the current in this coil to be in this direction, I. Of course, we have it as I here, downwards, and let the orientation of the line joining the point of inquiry and the radius be alpha. So this angle here is alpha. And of course, we are dealing with an element which is contributing to the magnetic flux density. Yeah. So if you do the geometry, you discover that actually this one is also alpha. If we took this to be 90 degrees. So we got that from Biot-Savart. Then we have that the electromagnetic flux density is equal to mu naught I over 4 pi. Then we have dl cross r roof, means below will be r squared. And we need to know that the element and the unit direction vector, this one which would have been along here, this is our r roof. So dl and r roof are perpendicular. Implying that then I can utilize this nice space on this other side. Yes.
I have some confusion with what we are having. That's the coil. Is its axis facing like that, or it's facing here like this? According to what we are doing, we confused about it.
The coil is like now, assuming this is a coil. The coil is now like this. Just squeeze this into a round thing. So this is our coil. And we are looking at the element being like this. So the element and the R are perpendicular. Because the element is on the coil like this, along the coil, we are taking an element off the coil, and then the line which is going to P, which of course extrapolates to the unit direction vector on a roof, is perpendicular to this element. So just because I can't draw it facing this way, just like when I used to draw by hand, if I was to draw my car, maybe not over the front. My car is not as good as this, but I'm only interested about the tires. So you would have to draw a tire, and just to show that kind of that it is twisted going this way, make sure that this other part becomes thinner. Then you have your rim, a couple of nuts, and then you have your I don't know how they call it, bricks. Are they called bricks? Tricks. These things which help on friction on the car. So this implies that if dl, so I think now you get a point. Yes?
The angle alpha, if it is the same alpha, it's like it has to be, the V component should be straight. For those alphas to be.
Yes? You have this coil, alright? We have the element here, we have the line here, and we get the angle alpha here. Alright? Then we have the dB there, and we have this alpha. I don't know whether you saw it.
So if you know it is like the whole thing here and the x-axis is 90.
Okay, so this would imply that my problem is one. that you just want to be spoon-fed. We are meeting next time, which is Thursday. It's as easy as we take it as it is. You go work it out and get the critical problem with it. And when we meet on Thursday, you are able to say, no, here on this point, the thing isn't working. But you are here busy trying to understand the thing. At the same time, you want to ask the question. In school, almost teachers never used to know that I exist until when they really tickle me so hard. Because I knew I had another chance to go and revise my notes. And if nothing would happen very well, I'm not saying that you don't ask. You have a right to ask. But ask for information. Ask to understand when you already have gathered something. I told you my teacher, if the one whom I met here, because I wanted more knowledge from him, I would do like an example, do some number halfway, then go there. He goes through and says, then I say, yeah, sir, that's where I got started. And then he unleashes everything and I understand everything. So if this angle is also alpha, I don't know where the problem is exactly. I don't know where the problem is. I haven't named any other angles that this is that, but I still believe that this angle here is 90. Okay, I guess everything is fine now. So then we have our, if the two, since the two, not that if the two, since the element, which is now if I can make the this gadget to be our coil, and then we have our element here. The line is here up to P. The angle alpha is this angle here, and after reaching here, the element which is along the coil is perpendicular to the arrows. And if they are perpendicular or at 90 degrees, their cross product equals to their magnitudes, which is the L magnitude times 1, and then the cross product gives you what? Which trigonometrical ratio of the angle? The sine of the angle. And what is the sine 90? So we get eventually this being the same as magnitude of the angle. I guess that you got it. So having that and everything is, but if you want to have this, I could say this is the F, then R sine 90 degrees, which is equal to 1 times 1 times the F. dB is equal to, so let's take the, this is this direction. So let's take the axis to be Z. So dB would be equal to dB prime dot Z, implying that our dB would be equal to mu naught I dL cos alpha divided by 4 pi e nu a squared plus x squared. Of course, where r squared was replaced with a squared plus x squared from Pythagoras theorem. Pythagoras theorem. I hope that is the, if I had Kasab, I would ask the other names of Pythagoras. And everyone would just go to lunch when you are again annoyed. So now I can say that, cosine of alpha from geometry, cosine of alpha would be the same as adjacent over the hypotenuse. And the adjacent is the angle neighboring the adjacent is the line or the side neighboring the angle. The hypotenuse is the longest. So that means that we get our adjacent A over the hypotenuse R, and R is A squared plus X squared square root, which we can replace root sign with to the power half. So this would imply that our B would equal to mu naught IA over 4 pi into A squared plus X squared to the power 3F integral from 0 to 2 pi A of dl. Why is it so? We are integrating our dl all through the whole coil, starting with a small element, maybe starting with nothing, which is 0, and we keep putting the pieces of this coil until when we finish it. And we know that the circumference of the coil is the same as 2 pi r. R for this case is A. So this implies that our B would equal to mu naught IA squared divided by, so this would culminate into, this is 4 pi into A squared plus X squared to the power 3 over 2, and then we multiply by the L from 0 to 2 pi A, which gives us, and I get the 2 to go here, the pi's to go, and I get my, I think this should be A. We still 8,000 squared yet. So we get our mu naught IA squared divided by 2 into A squared plus X squared to the power 3 over 2. That is for only when we consider one strand of the ring. If it was just a ring of one strand, like one piece of wire, and then you put it. But now if we got a number of them. So if we got a number of them, like I have drawn here. So for a coil of n turns, it's got a couple of, turns or strands. Then we would have that we would get our B being the same as mu naught NI A squared over 2 into A squared plus X squared 3 over 2. So we've been able to apply at least to these two examples, and you sure did this example in electricity magnetism and also in magnetism in high school, using this color methodology, and everything came out as we've got it. But there's one thing that we can take note of, that if we were to move further and further away from the coil, that is, if X becomes as large and large as possible, then we would have that as X becomes larger and larger than A, that is, you're moving away from the coil and going further and further, it means you have your this inside one, what remains? So you have x squared, which goes with this, so it becomes x cubed. What is the significance of this? You remember in electrostatics, when you had a line charge along your coil, if you move the farther away you get, or it will be assumed as if you are having a point charge from this ring. Because the farther you go away from a big body, like the way we look at the sun to us is a small dot, isn't it? Really. But the sun is the hugest element in the galaxy or in the solar system. The hugest of all. So, as an exercise, I will say, what is the significance of moving away farther from such a coil? Any questions? So quick. But I'm not surprised. It sounded like a lady, meaning that no is always the first response. By default, is it Raima? By default, she's supposed to say no until further notice. So the divergence and the curve, we use the capital D. The divergence and curve of D. So if you have a bunch, just like we did for, this is the beauty about electricity and magnetism. Because when you make charges go in motion, you produce a magnetic field. Similarly, when you make charges move within a field, they produce electricity. That is, if I get charges to move in the current connector, as I showed you on the cardboard, when the wire was pinpointing through the cardboard and you put the iron filings, you are able to get or to commodify that the iron filings make concentric circles which are designed or an outline of the magnetic fields. At the same point, when you got your magnet, if we can just take an example of the horseshoe magnet, if I can make it maybe a little further, and you know, within this shoe magnet, you put two rays. So if this is your north, this is your south, because you got a little bit of field going down. So if you were to have two rays in here, another ray here, and you connect these to a Sena zero galvanometer, and you make an aluminium ray to, you slide it on the other side, depending on where you slide it, then you get a key in your galvanometer. It's something easy to do, maybe we can do it in our laboratory. But I'll make sure I demonstrate to you this when we reach the electromagnetic induction. I'll show you, first of all, how a coil can be set in motion without even touching it. You should be able to do that. Keep reminding me. So as you can see, you make motion of this. If you move it, you have to use, because you are going to use force, you have to learn how to do these things without any hassle. Okay, so we use the field is the first finger, so I will have to go down. The current is nowhere, it's what we want to get. The motion is the thumb. So that means my current will be in this direction. So once I slide it this way, the current will move in this direction and the deflection will be in that direction. I move it this way, the current will be in this direction. So there is a kink. You see, that's why the two are related. When we talk of electric field intensity, we are talking of charges. We talk of magnetic field, we are talking of magnetic field lines. And these two are inseparable because one, that's why maybe I don't use that example and they are conjunced. So one, under the divergence and the curl of B, we looked at the curl and divergence of E. That is for electric field lines. We looked at the charge, which was having tantamount value of electric field lines emerging out of it, assuming it was positive. And we tried to curl them. And when we curled them, we made them both go elsewhere. And when we curled them, we got what did we get? Zero. Because when we tried to curl them, bend them, we couldn't get any further electric field energy going out. But when we took the divergence, when we tried to diverge them, make them go further, that is divergence of E. What did we get? Depending on the charge available within the vicinity, we were able to get epsilon. So it was dependent. You can only go as far as you wish, depending on the charge density you get and how permittive the region you are within is permittive to your electric field lines. The same stuff is what we're going to do for the magnetic field lines. So let's look at the Ampere's circular law. Ampere's circular law. And we consider a straight wire carrying a current I perpendicular in paper, perpendicular in my blackboard. I can take off the blackboard. You gotta have the freedom to say paper. So in the page, since you'll be reading your notes, but I can sure say in my chalkboard. So if it is in a chalkboard, it means if I hold the wire and curl my fingers, it means I'll be looking at the screw from the top, this screw which we drew yesterday. So I'll be looking at the star from the top because I'm going, the page. So I got this as the symbol, and then I can draw my concentric circles. My fingers, because this is pointing into the blackboard, my fingers are having the, so I go up. Draw another one, up, down, another one. I can draw as many as possible, but I'm hungry enough not to draw many. I can stop at those. So then if we consider a straight wire carrying current I in relation to the page, then at a distance r, from the wire, First of all, we got that the magnetic flux density at a point R from this wire. If we, let's say we took around this point and it is a distance R, our B is the same as mu naught I over 2 pi. Y was the distance, perpendicular distance from the point to the wire. But for this case, our perpendicular distance is this R. So this is our magnetic flux density felt at this point. So B is equal to mu naught I over 2 pi R for a point distance R from the wire. So from the integral B that dl is equal to, that is in a closed, if you took one strand, I took one strand where the distance from the center, from the coil is at a distance R. So B that dl would be equal to integral over the closed, that closed loop, and then we have our B as mu naught I over 2 pi R into where C is a circular path, of radius R. Hence, integral B dot dl over the curve, closed loop, is equal to mu naught I over 2 pi R into you are integrating along the whole of this loop that we are taking, this loop which is the radius, this is our C, radius R. To move along it, you have moved along the circumference of a circle radius capital R, meaning that the total length after integral would be 2 pi R. Thus, we would have that the integral over the closed curve C B dot dl is equal to mu naught I. And this is something special, and the result holds for any closed path. The result holds for any closed path C threaded by current I. In generally, integral B dot dl is equal to mu naught I. This should be enclosed current. So if you look at the current enclosed by this region, this is our general expression. And We can call this one equation 1, where this enclosed current is given by, if you remember previously, integral over the closed or within this closed path S J dot, yes, where S is being, or is the S being the open, where S is the open surface bounded by the curve C. Bounded by the curve C. Any queries so far? Equation 1 is called Ampere's circular law. Ampere's circular law. Ampere's circular law. So by Stokes' law, equation 1 becomes integral. So we are going to transform this line integral into a surface integral. And that would mean that we will have that our integral b dot dl would be the same as we take the curve of the vector and then dot it with the surface, with the s. So this would be the same as, double integral for the surface, the curve of b dot, yes. So we got this as equal to mu naught I. Thus, we would have that our integral over a closed surface S. So this is now our surface S. This was a loop or a path C transformed into a surface S. So that we get our surface S, the curl of B dot ds would be equal to mu naught integral, that is mu naught I, but I is the same as integral here over the surface S, the current density dotted with yes. And if we collect like terms, since they are all integrated with respect to the surface, then we get our integral over the surface S. Then we have the curve of B minus mu naught J. Then ds that ds equals to 0. Implying that our curl of B, this is not good at all. So the curl of B is equal to mu naught J. This is also special. We can call it our equation 2. The specialness in it is that compared to the one we had, the circular law we had here, which I've just wrapped off, integral over the closed loop d dot dl being the same as mu naught I enclosed. This equation 2 is the differential form. Differential form of Ampere's circular law. So you never know. I can ask either for you to state, if I just say state Ampere's circular law, definitely I'm talking about this. But if I am too specific and I say state Ampere's circular law in differential form, then I mean to go to this other one. So just to conclude this part of the curl of B, we got a note that it holds only for steady current. Only for steady current if D is equal to mu naught H. Then we will say that our curl of H is equal to J. Because if B is equal to mu naught H, so we put here mu naught H, mu naught goes out, cancels with the other mu naught on the other side, and we get curl of H equals to J. Where H is the equivalent of this baby here. So just like we say B is equal to epsilon A, then we say B is equal to mu H. So where H has the same name as the one which is electric. So you just say magnetic field intensity, whereas the other one was electric field intensity. So we get this H, the magnetic field intensity. So, on Thursday, we shall look at divergence. I guess we have been looking at the curl. All along we are looking at the curl, so Thursday we shall look at divergence. Enjoy your lunch.